Hello everyone, this is week 7 video and today we're going to discuss about integrals which are of the form of negative infinity to infinity of f of x dx. So more specifically, we're going to discuss this type of integrals and also we're going to discuss why are they defined in a specific way. First, let's think what is the point of defining an improper integral in an infinite interval. To answer this question, let's consider very simple cases of two familiar examples, integral from 1 to infinity of 1 over x and from 1 to infinity of 1 over x squared. Maybe you saw these integrals by now, or maybe you'll see them soon. So you know that if you saw them, you know that these two, like one of them, this one, 1 over x, is divergent and this one is convergent. If you look at the graph of these two functions, you'll see that the graph of these two functions are almost the same. So what is the reason that one of them is convergent and one of them is divergent? The only difference is that 1 over x squared goes to infinity or approaches 0 or that approaches the x-axis much faster than 1 over x, so that the area below the graph restricted by the graph and x-axis for 1 over x from 1 to infinity is infinite, but the area below the graph of 1 over x squared and above the x-axis is going to be a finite number. Why is that? If we compare these two graphs for small numbers, it's impossible to see a huge difference between them. But if we compare the graph of these two functions for very large numbers, for example, for 1 million, if we consider x equals 10 to the power of 6, 1 over x is going to be 10 to the power of negative 6, and 1 over x squared is going to be 10 to the power of negative 12. So you see that the difference is going to be huge, but this is not even enough if we consider, if we compare 1 million with infinity. So at infinity, 1 over x squared goes to 0 much faster than 1 over x. So roughly speaking, the goal of defining the improper integrals on infinite intervals is to check if the graph of the function gets close enough to the x-axis, especially when x approaches to infinity or negative infinity. So pay attention to the word close enough. So for example, 1 over x, it gets close to the x-axis, but it's not close enough to make the area below 1 over x and above the x-axis to be finite. Now let's remember the definition of these integrals from negative infinity to infinity of f of x dx. By definition, we need to split this integral into two pieces. For some a belongs to r, so you define them this way. For some a belongs to r, and this integral is convergent only if both pieces are convergent. So now let's see what is the reason for this definition. For example, why aren't we define this like this? Limit of b approaches infinity from negative b to b, f of x dx. Why not? And some people have a tendency to actually use this wrong formula to evaluate this integral. So let's see why is this formula wrong. So let's use that wrong way to evaluate the integral from negative infinity to infinity of x dx. So if we use that wrong way, I'm going to write that the limit of b approaches infinity from negative b to b x dx. So you know that the graph of y equals x so the graph is, or the function is an odd function. So obviously when you find the integral from negative b to b, like this area is going to be positive, this is going to be negative, and they are the same areas, but one piece is above the x-axis, the other piece is below the x-axis, and they cancel each other, and the answer is going to be 0. And if you calculate this, you see that the answer is 0. But considering the goal of the improper integrals, does this make sense? The answer is no, because as you see, not only the graph of y equals x does not get close to x-axis, but also it gets actually far from x-axis. It's just like, you see, the distance to x-axis become larger and larger from both sides. So this does not make sense here. Let's see another example. So let's do the same thing for negative infinity to infinity of sine of x dx. Again, if we are using the same wrong way, we end up with 0. And again, it's very easy to check this, or you can use the symmetry of sine of x, because sine is an odd function, and if you integrate an odd function over a symmetric interval, then the answer of that integral is going to be 0, or you can directly calculate this, and you'll see the answer is going to be 0, which does not make any sense again, because as you know, graph of sine of x does not get close to x-axis all the time, but it's alternating like this. And it doesn't matter how large x is going to be, this alternation is going to be repeated and repeated. The right way to check this integral is to split the integral from negative infinity to infinity into two pieces, from 0 to infinity sine of x dx plus from negative infinity to 0 sine of x dx. We usually use 0 because it makes the calculation easier, not always, but most of the times, but you can use any real number instead of 0. So let's evaluate this integral from 0 to infinity sine of x dx. So as you see, when we evaluate this integral, again, I leave the calculation for you to check, we end up with this limit. And as you learned last semester, this limit does not exist because cosine is a periodic function, and when b approaches to infinity, we cannot end up with a specific number for this. What does it mean? It means that this limit does not exist. By definition of the improper integral, it means that this integral is divergent, which means that the integral from negative infinity to infinity of sine of x dx is divergent. Remember, the definition was saying that this integral from negative infinity to infinity is going to be convergent only if both pieces are going to be convergent. So even if one of them is divergent, it means the whole thing is divergent. So you see, this is giving us the right answer because, and it makes sense because sine of x does not get close to the x-axis all the time when x approaches to infinity. Roughly speaking, we want the improper integral gets close enough to the x-axis from both sides. If one of the two integrals is divergent, then it's enough to conclude that the improper integral is divergent. So this is just a note about why we check only one piece of this and we decide it's divergent. I want to give you a warning here. As you see, sometimes I use some words like getting close to x-axis or getting close enough to x-axis. I'm using these words just to give you some imagination about this type of integrals, but we should not use this as an argument. In order to prove or to show some integral is convergent or divergent, we must follow the definitions. And if you use such arguments in any test or exam, you are not going to get any point for that. Okay. So let's see another example. So this time we want to check the integral from negative infinity to infinity of dx over 4 plus x squared. We want to check if this integral is convergent or not, and if it's convergent, we want to evaluate it. we're going to use the definition, and we are going to split it into two pieces from 0 to infinity, dx over 4 plus x squared plus negative infinity to 0, dx over 4 plus x squared. Now I'm going to start with this part, the integral from 0 to infinity, and I'm going to write the definition for it, and then I'm going to evaluate the integral. I'm going to leave it for you to check that the antiderivative of dx over 4 plus x squared is 1/2 tan inverse of x over 2. It's very simple to check. So when we find the antiderivative, we have to apply the fundamental theorem of calculus and plug b and 0. And this will give us 1/2 tan inverse of b over 2 minus 0, because tan inverse of 0 is 0. Then when you let b approaches infinity, so here you need to remember the graph of tan inverse to be able to evaluate this limit. Remember that graph of tan inverse looks like this. So this is pi over 2, and this is negative pi over 2. So as you see, when the variable goes to infinity, tan inverse goes to pi over 2, and when the variable goes to negative infinity, tan inverse goes to negative pi over 2. So here, because when b approaches to infinity, b over 2 also approaches to infinity, so it means that we want to find tan inverse of infinity, which is pi over 2, and then pi over 2 multiplied by half, it's going to be pi over 4. So this means that the integral from 0 to infinity dx over 4 plus x squared is convergent, and its value is pi over 4. Now, it's very easy to check that the integral from negative infinity to 0 is also convergent, and its value also is pi over 4. You can check it. It's very easy. You can use a direct calculation similar to what you had in the previous slide, or you can do some sort of like discussion about the fact that the graph of 1 over 4 plus x squared is symmetric with respect to the y-axis, and actually this function is an even function, and you can use such an argument also, but it's very easy also to do the calculations. So now, since both pieces of the integral, I mean from 0 to infinity and from negative infinity to 0, both of them are convergent, we conclude that the integral from negative infinity to infinity of this function is convergent, and then we add the values that we got for each one of those pieces. So we add pi over 4 plus pi over 4, and the answer is pi over 2. So this is the value of this improper integral. So now here I have to give you another warning. So if we try to solve the last improper integral, that integral from negative infinity to infinity of dx over x squared plus 4, using the wrong way, we will still get the correct answer. But this is just a very special integral, and this is just random. This is just an accident that we get the correct answer using the wrong way for this one. Even if you get the correct answer, you must avoid that wrong way. So I'm going to stop here. Have a nice day, and I will see you on the next video. Bye.